Hello. This is the second part of chapter 2. In the first part, I defined conditional probabilities and we learned how to calculate conditional probabilities from the joint probability distribution table. It was intuitive. And then we learned a very important concept of statistical independence, which is really, really important. And later, we are going to use the independence again. So, and also we learned how to check statistical independence from the data or from the probability distribution table. Today, as I said last time, we are going to consider conditional probability in a different way. So now we will be considering the other way. So conditional probabilities are given. So your information is given as uh, conditional probabilities. But given the conditional probabilities, you'd like to uh, obtain a different form of probabilities. So we will study how to do that. To motivate, let's think about an example. Here, let's think of a smartphone manufacturer. Maybe you may change the name, like say electric vehicle manufacturer or I okay. So smartphone manufacturer is concerned about defective batteries. Suppose that you are in charge of the quality control. So you need to minimize or you need to uh, calculate how many of your manufactured products are defective. So you are particularly worried about defective batteries. And so the information now, so as say, imagine you are in charge of that, and the information given to you is first, you know that there are two types of batteries used in the manufacturing, and 60% of them are domestically produced, and 40%, the other 40% are imported. So we are going to denote domestic battery as D. D is the event that a randomly chosen battery is domestically produced. Automatically, the complement is imported battery, and we will use F to denote a defective battery. So you have a lot of batteries to be used for manufacturing, and you are categorizing them into domestic batteries and imported batteries in one dimension. And in another dimension, you are dividing them into defective batteries and good batteries. So let's see. Also, you know that domestic batteries are better in terms of defect rates. So only 2% of domestic batteries are defective, but among imported batteries, there are 7% of defective ones. Okay, so these are the information. So the first information is the proportion between domestic batteries and imported batteries. And second information is about the defect rate of each type of batteries. Then, so this information, the second information, defect rate, how can you express these probabilities using our notation? Think about that. So you have to understand what these probabilities are, and also you have to be comfortable with the notation. So think about that. I'll turn the page. 3, 2, 1. The answer is like this. So let's think about this. 2% of domestic batteries are defective. When I say this sentence, obviously 2% is a probability. But how do we get the probability? the experiment would be like this. Here is a pile of domestic batteries. You already know that those batteries are domestically produced. So that's the condition. That's what you know. That's what already happened. So given the condition that those batteries are domestic, you randomly choose one battery and see if that battery is defective or not, like do some inspection. So that's how you get a probability. That's the underlying experiment for this this sentence, the probability in this sentence. Therefore, we can think about the structure this way. We we have a condition that the battery is domestic, and we are interested in the event of defect, the result of inspection, whether it is defect or not. And here, so 2% is the probability of a defective battery among domestic batteries. So distinguish the condition and the main event of our interest. So that's the important part, what I want you to understand. And in the same way, excuse me, you can think of 7% as the probability of defective batteries among imported batteries. So condition is the complement imported batteries. Given the condition happened, F is what you are calculating the probability for, right? Okay, so anyhow, this is the information we have as a manager, say in the factory. You know these probabilities. This is what you want. This is what you have, but what you want is different. You need to calculate the overall defect rate. Overall defect rate would be written in this way: probability of defect batteries. So uh, it doesn't matter anyhow in the final product. It doesn't matter which battery is used. What's important is whether it is defect or not. So unconditional probability is important, and also it'd be, you may want to see the probability of domestic batteries given defective ones among defective batteries. So like maybe you need to do this to negotiate with the battery producers. Anyhow, so what we want to do here is we have some conditional probabilities, but the information we need is a different type of probability, like this. So what's given is this and this, conditioned on D or D complement, but what you need is unconditional probability or conditional probability using a different event as the condition. So that's what we want in this example. Uh, More fundamentally, it it these two probabilities can be obtained if you know the full joint distribution table. If you know the full joint probability distribution, then calculating probability is not a problem. We learned how to do that. So we are going to change our problem to this. Given the conditional probabilities, given the information, we would like to recover the full probability distribution table. This table. That's what we would like to obtain in the end. So here it sounds a bit more complicated. It is more tricky. So I will introduce you an interesting intuitive method to do that. It is called tree diagram method. So we are going to use a tree diagram method. So we will draw a tree diagram. So I want you to have a paper and a pen and paper in front of you, so that you can follow what I do. So the tree diagram method goes like this. First, we will imagine a certain number of experiments. So for example, we will assume that there are 1,000 batteries. It doesn't matter what number it is. 1,000 is just an arbitrary number, but of course, you should choose a simple one. If you choose, say, several billion or million, then your calculation will be more difficult. So having 1,000 or 10,000 would be useful for your algebra. So let's think about 1,000. It doesn't matter even if you choose a different number like 100, 10,000, 1 million. The result should be the same. Just imagine you have in front of you, imagine that you are inspecting 1,000 batteries, 1,000 batteries, and I'm going to classify 1,000 batteries according to the given probabilities. So the probabilities are given, say first. So we have two types of information. First, we know the ratio between domestic and imported batteries. And second, we know the defect rates for each type of batteries. So we are going to use these two types of information, and one is unconditional. This ratio, 60 to 40, this ratio is unconditional, right? It's unconditional probability. We are going to use this probability first, and then given each condition, we will use the conditional probability. So you will see why I need to do that, why we have to do that way. So we are going to, anyhow, the point is we will classify the imaginary 1,000 batteries into different outcomes, categories. And finally, you will divide the batteries into four different categories, into these four types. So right, so X is the number of domestic batteries, defective domestic batteries, and Y is defective imported batteries, and Z is good domestic batteries, and W is good imported batteries. So in the end, you will have four types, and so in the end, 1,000 batteries will be classified into these four types, four outcomes. That's what we are going to do. Uh, let me let me show you what we do in the next video. Already it's 30 minutes. Okay, let's see you in the next video.